steps support assignment number 7. This was the question. Now, you've probably noticed that this video is going to be quite long, and that's because this is a tough question, but it's also really, really good and really important maths. And so what I'm doing is going to make sure that I explain everything as carefully as I can, because there's no point in me rushing through this and just, with no one understanding any of it. So I'm going to go through this as carefully and precisely as I can, because it's really important maths, and otherwise no one's going to learn anything anyway. So let's get into it. So this is a function, x to the power n plus a1 x to the power n minus 1, and so on down to an. Now these a's, these a1s to an's, those are just numbers, and the n is just whatever power above the x. So let's just look at a couple of examples of what this could look like. It could look like this, right? So I've chosen n to be 8. I've chosen a1 to be 4, and said n minus 1 is therefore 7. And then I've skipped x to 6 because it doesn't say the a1s have to be non-zero. So this could just be 0 to x to the power 6. Also, the a's could be negative, so you then go down to a 5, and then I've just said an is 5 at the end here. So that's one example of what it could look like. This is another example. Now this is what's called standard polynomial form. So this is in standard form. Now there's another way to write polynomials, which is in factored form, which is what the question is saying f of x can also be written. So here's factored form. And now you might want to notice here, this is the question from assignment number 4. And this is standard form. And then this was our effort of putting into factored form. And now notice how these k's, these are different coefficients to the things up here, to the a's. But they are related, and the relation between these k's, which are the things in factored form, and the a's, which are in standard form, that's what this question is kind of about. So here's the thing here, here's the question. So we've got that big piece of algebra there, and we've got that equals this in factored form. Now by considering f of 0, so f of 0 is just what happens when you use x is 0. So 0 to the power n plus a1, 0 to the power n minus 1 plus a2, 0 to the power n minus 2, and so on, and all the way down to an. Now, what's good about this is that 0 to the power anything is 0, so all of these terms are just going to go away. Now, the term immediately before a to the power n, a to the n, is a n minus 1 x. But that x is also going to go away because x is 0, which means all I'm left with is just this last term of a to the power n. And you can notice, that's what happens when you do here. If you put 0 into that, all of this goes away, and you're just left with a 5. Put 0 into that, all of it goes away because the last term is actually a plus 0. So this whole thing equals 0. And likewise here, put a 0 into that, all of that goes except for the plus 4. So the only thing that's left is the last term, an. And look what happens over here in factored form, where you just put in zeros into here, 0 plus k1, 0 plus k2, all multiply together, and you just get k1, k2, k, and so on. And now this seems new, but we've seen lots of this before, because all this is saying is, if you take the numbers in factored form and multiply them together, you get the last thing from standard form. And we've kind of done this thing before. If you expand this out, the very last term is going to be minus 1 times minus 4 times plus 1, which is plus 4. Right, so that's all this is saying. Next thing, show that this equals this. Now, what do we see here? Well, look at this factored form bit. The only difference between that and the original factored form is that the x has become a 1 in every bracket. They've also swapped over, but it doesn't really make much difference. The x has just become a 1. So let's do f of 1. Let's make our x 1. Now in standard form, we get 1 to the power n plus a1, 1 to the power n minus 1, plus and so on all the way down to an. And now this is also good because 1 to the power anything is 1. So this just equals 1 plus a1 times 1, which is a1, plus a2 plus a3, plus and so on until an. Now in factored form, putting 1 into here, we get 1 plus k1, 1 plus k2, 1 plus kn3, and so on. And now this is almost what they want, except they've just swapped the order, like I said. So I'm allowed to swap the order, and I'll swap it. And this is our second thing, which just says, in English, that the sum of all of the coefficients in standard form equals the product of all of the factored form numbers added 1 first. And you can check this works on this one here, right? The one we did in assignment 4. The sum of the coefficients in standard form is 1 minus 4, which is minus 3, minus 1 is minus 4, plus 4 is 0. So in this thing here is 0 for this one. And now in factored form, what does this equal? Well, our k's are these numbers. So our first k is minus 1. Well, minus 1 plus 1 is 0. So this bracket is 0, which means no matter what these are, because it's all multiplying, this whole thing is 0, and we get 0 equals 0, which is good. So this clearly works for this as well. Okay, so those are the two things I've got so far. The third thing, give a corresponding result for k1 minus 1 times and so on. Now, again, notice in this factored form here, the only difference is that that x has become a minus 1. So that gives us a pretty good hint that we want to be using f of minus 1. So let's put that into standard form, and we get minus 1 to the n, plus a1 times minus 1 to the n minus 1, plus all the way down to an. And now in factored form, like I said, we just put minus 1 into here, and we get minus 1 plus this, and so on. Now, this isn't what this looks like, but again, they've just swapped the order. So I'm just going to swap the order on that factored form there. So again, factored form on one side, standard form on the other. So I've swapped the order there, and now let's go back to this standard form here, because this is a little bit weird. Now, I don't know what minus 1 to the n is, because if n is even, then it's positive 1. If n is odd, then it's negative 1. So I don't really know what this is, but I do know what an is. It's just an, because it has no bearing on this minus 1 bit. It's on its own. So what I'm going to do is I'm going to start at this end and say f of 1 is an, starting at this end. Now the term before it would have been an minus 1 times minus 1 to the 1. And the term before that is an minus 2 times minus 1 to the 2. And the good news is I can actually know what these are. So let's go from this end working this way instead of that way. So an plus, and now this is just minus 1, so it's minus an to the minus 1. And then this is a positive 1, so it's plus an minus 2. And then these signs you can see are alternating, so we go minus, plus, all the way to the end, and we still don't know what this is. But that's fine. This is as close as I can get to the corresponding result. Right, so I'll just leave it there. Okay, so those are my three results. We can look at them if you want to. You can also test all three of them in this one if you want to, but they should all hold. Those are my three results that link the coefficients in standard form to these numbers in factored form. Right, those are my three good equations there. Okay, so the next part of the question then, find the roots of this. Now, you might look at this and think, well, I know for quadratics that I have the quadratic formula, which I can use to solve for roots, which means there's probably a formula that works for quartics, which is what this is when you have a power of the 4. And the good news is you're bang on, and here it is. So if you'd like to, you can assign this coefficient as A, this one as B, C, D, E, and just substitute in and unpause the video when you're done, and you can check your answer against mine. Except please don't do that, obviously, because this is horrific, and because step questions never ask you to just leave information behind. If you've worked out all these things in the first part of a step question, you don't just abandon them just because there's another thing. You're going to want to use these, right? So let's use these to solve this question. So what are these saying? Well, we've got the function, that's the function they've given us, and I want to write this in factored form because, again, we've been talking about factored form a lot in this video. So I want to write this in factored form. Now, it's going to use precisely 4 brackets because it's an x to the power 4, so I can know it's 4 brackets long. And now what I'm going to do is I'm going to try and figure out what these k's are, because if I knew what these k's were, now the k's aren't the roots, but they do give me the roots, right? For example, if this k1 was just 3, then I'd have a bracket that was x plus 3, and the root would be at minus 3. So the k's aren't the roots, but they do give me the roots. And they're very closely related to them. So let's try and find the k's here. I'm going to try and solve for k's, and I'm going to use these rules to do it. Now, the first rule says an, the last number in standard form, equals all the k's multiplied together. So that's nice and easy. And I could have got that by just using f of 0 again. Putting 0 into here gives me this thing here, 576 is equal to all the k's multiplied together when the zeros go in there as well. The next thing tells me that all the coefficients added together, the first coefficient is just 1 by choice, all the coefficients added together equal 1 plus each of the k's multiplied together. So let's add all the coefficients together, 1 plus 22 plus 172 and so on. They equal 1 plus all of the k's each multiplied together. Okay, tidy that up, and I get my second important equation, which I'm colouring in, because these are the important equations. The third rule, now it's probably easier just to use f minus 1 again to see this third rule. Just put f of minus 1 into here. We get minus 1 to the power 4 is positive 1. Minus 1 to the power 3 is negative 1 times by 22 is negative 22. And so on, minus 1 squared is positive 1, so we add 172. And then again, we put minus 1 into our factored form, and we end up with this. And we tidy that up, and we end up with our third important equation. So those are our 3 super important equations that we're going to use to solve for all of our k's, which will then give us our roots. Now, we have another problem. I mean, this question is just a landslide of gut punches, but we have another problem here, which is that there's a principle, a really important principle in algebra. I can solve this equation up here. And I can solve it because there's one unknown and one equation. I can solve these equations because there's two unknowns and two equations, which essentially means I have enough information for the number of unknowns. So I can solve this. I can't solve this because I don't have enough information for my number of unknowns. Right? I can find solutions to this. If x is 1 and y is 1, that works. But also if x is minus 1 and y is 3.5, that also works. So I don't quite have enough information to pin down x and y. I don't have enough equations. And now here's a problem, because when we look at this, we think, well, how many things am I looking for? I'm looking for 1, 2, 3, 4 things. And how many equations do I have? 1, 2, 3. So this is bad news, because I have too many unknowns for the number of equations that I have. But this is where we realize it's not about the number of equations. It's not about the number of equations. It's about the cones. No, sorry. It's about the amount of information that you have. So it's about the amount of information the question gives you. I've got these 3 pieces of information, but I also have a 4th piece of information. There it is in the question, given that they are all integers. That's my 4th piece of information. And I can use that and make this solvable, right? There's my 4th piece. And in fact, I'm going to lean incredibly heavily on this piece of information here. This is going to be incredibly important to me. So usually when you solve stuff like this, you're used to doing some algebra, you multiply up, you do some elimination, maybe some substitution, and you do all your algebra things, rearrange and stuff, and you find your answers. I'm not going to do any algebra on this. I'm not going to rearrange these or substitute them. I'm going to lean incredibly heavily on this and do what's called number theory. And so I'm going to go through the rest of it quite slowly because you haven't seen much number theory before, and I'm going to try and explain exactly what I'm doing. So there are my 3 equations with the 4th piece of information here. Right, let's look at this number here, 576, because what this is saying is I've got one number times another number times another number times another number equals 576. Now, normally, there would be an infinite number of things that I could use multiplied together to make 576, except all of these numbers are integers. Right? They're all integers. So there's actually a limited number of things I can multiply together to make this. And let's find out what they are. So 576, as an example, now what I'm doing here is I've broken it up into its prime factors. And what you can think of that I'm doing here is I'm kind of distributing out the prime factors in 4 different places. So I'm giving 1, 2 to there. 4 2's can go here. That uses up 5 in total. My last 2 can go there. Bind it to a 3 to make a 6, because 2 times 3 is 6, use the last 3 there. So I'm kind of just distributing out these primes in such a way that I get 4 things multiplied together, which is what I have here. Another way I could have done it is use 1, 2 there, 3 of them go there, 2 of them go there, so I've used 6 in total, and then the 2 3's go there to make 9. Another way is this, 2 2's go there, 2 2's go there, 2 2's go there, and 2 3's go there. Now the problem here is, if we look at these examples I've got, there's no single number that appears in every one of these lists. So I can't just say, well, one of these k's has got to be something over here, because there's no number that appears every time. I can't say for sure. So let's just move on to the next equation, see if I have any luck there. So this is 3 cubed minus 7 squared. If you break that down, and again, distribute this out. So 1 3 goes there, 1 3 goes there, 1 3 goes there, the 2 7's can go there. So that's one example I could use. I could also use this, where 2 3's go there, the last one goes there, the 2 7's are separated. Now it's tempting to say, well, do I always need a 3 here? But no, you don't, because you can be super sneaky here and say, actually, you could use a 1. Put all the 3's in there, and then the 2 7's there. And now we can see we don't have a common number in every list, so we can't just say one of these things. Now, I should have said as well, this is one number. 1 plus k1 is one number multiplied by another number, multiplied by another number, and so on, is equal to this. So I'm breaking it down to 4 numbers, just like I did here. I'm going to do the same here again. This is one number times another number times another number times another number is 175. So let's break down the 175. And this seems more hopeful for a second, because there's only 3 primes that make 175. 2 5's and a 7. So I break that down and I think, well, I need 4 things to multiply to make this. So how do I do that? Well, I use this trick, right? I use the 1. So I put a 1 in there. And now it's tempting to say, well, actually, I think I always need a 1. because there's only 3 primes being used. I think I always need at least one 1. Even if I group those 5s together and use another one, I need at least one 1, right? And now, again, time for another gut punch that this question is going to give you, because although we're so used to talking about factors as being positive, the question is just talking about integers. So I could say 175 is that, and now I have a list that doesn't involve a 1. So I can't actually say for sure that any numbers. I can't assign any k's to anything yet. So I need to be more thorough in my search. So how am I going to do that? Well, again, let's break down 175. I've done that before. And now let's just list out entirely all of the factors of 175. There they all are. And I've just done these as examples just to show you how to break down those things. And these are the factor pairs, aren't they? So I've broken down my factors into these here. Now, those are the factors, but remember, this question is just talking about integers, not factors. So I can also say that these could be the things that multiply to make 175, they could be all the negatives as well. So those are all the possible integers that can be used to make 175 out of these 4 things. Now, if I list those out like this with all the positives first or the negatives second, now I can say, well, what would the k's have to be? If these are the only numbers that I can put into these brackets, what does the k's have to be in each case? So for example, if I was making this bracket 1, what would k have to be? Well, it would have to be 2, because 2 minus 1 is the 1. What if I was to make this bracket 5? Well, I'd have to make the k 6, because 6 minus 1 is 5. So I can say my possible k's, I just have to add 1 to each thing. 2, 6, 8, 26, 36, and so on. Right, so those are all of my possible k's for the green equation. Now let's do the same with the blue equation. So there's 1, 3, 2, 3. Let's list out all of the factors. Now I haven't listed them all because I can't be bothered, but you'll see why in a second. Now again, we're not just talking about factors, we're talking about any possible integers that multiply. So it could be the negatives as well. And now think again, what do the k's have to be in the blue case here? Now if I'm making this bracket here 1, what does the k have to be? Well, it has to be 0. And if I'm making this bracket 3, what does the k have to be? Well, it has to be 2. So I actually end up, and if it's 7, then I have to make the k 6. So I end up taking away 1 from all of those to give me my possible k's in the blue scenario. Just take away 1 from all of them. And now, what we need to think here is, well, actually, I need all 3 of these equations to work. Right, that's what a simultaneous equation is, essentially. I need all 3 of them to be correct. So not just the correct case for this one, but also for this one. So whatever k's are possible here, they must also be possible here. So I'm only interested in the k's that are in both lists. And what k's are in both lists? Well, I can see a 0, a 2, a 6, an 8, a 26 is in both lists, and a -4 is in both lists. And those are the only things. Right? So in both lists, so I've narrowed down my k's, any of my k's, my k1, k2, k3, k4, they can only be any of these 6 things, because those are the only things that satisfy both of these. But of course, I've got one more equation to play with, the red one. So let's break down 5, 7, 6, that's 2 to the power 6 times 3 squared. Its factors, therefore, are all of this. Now again, not just talking about factors, I could also use the negatives. And now we need to think, well, actually, there's nothing to change about k here. Like I'm just multiplying the k's together. So I'm actually the k's are just these numbers, right? The k's are just those numbers. So it's all of these plus all their negative counterparts. And now we think, well, here's the list that I've already got. They're in both the red and the green and the blue. Are any of these eliminated because they also have to be in here and they're not? Well, 0 isn't in here. So 0 is eliminated. And also 26 isn't in here. So 26 is eliminated. So the only 4 values in all 3 lists are 2, 6, 8, and -4. So those are the only things that k can be. Any of my k's can be. So k1, k2, k3, and k4 are some combination of 2, 6, 8, and -4. Now to find out which one they are, I'm just going to test them, because I've got so few options here that testing isn't too bad an option. So let's take the red equation and let's put them in. So remember, I've already broken this down. It's that, right? 2 to the 6 times 3 squared. Now, let's think carefully about this, because if the k's can only be this, where are these 3's coming from? Well, the only number that has 3's in it is this one. These are all just made up of 2's. So this one has 3's in it, but 6 only has 1 3 in it. It's 2 times 3. Now, I apparently need my k's to have 2 3s in them. So that means I know I'm going to have to use 2 6s, because each 6 brings with it 1 3, and I need 2 3s in total. So I know that 2 of my values, and the other way to look at it is just break this down into 2 to the power 4, and then another 2 2s, another 3 3s, and then 2 times 3 is 6, 2 times 3 is 6. But I know, logically, that 2 of these values now must be 6s, because otherwise I'm not getting those 3s from anywhere. And now what am I left over with? Well, I'm left with 16, because 16 times 6 times 6 is this. So whilst 2 of these k's are 6s, I don't know what the other 2 are yet. But again, I can trial and error this. What are the only ways to make 16 out of 2 of these values? Well, I can't use the 6s anymore, because 6s contain 3s and 16 doesn't. The only way to make 16 is using a 2 and an 8. So I could try this, 2 8 6 6, or using 2 negative 4s, because they'll also make positive 16. So I'm finally down, this is a bit like a proof by exhaustion, I'm finally down to 2 options, either this one or this one. These are the only 2 options that work for the red equation, using some combination of just those things. So how do I know which it is? Well, again, like I said earlier, I don't just need to satisfy this equation, I need to satisfy all of them. So let's check out this green equation. Let's label this one, it doesn't matter which way we do them, but let's just do K1, K2, K3, K4, and let's see whether these work in this equation here, because they have to, right? So let's put them in. 2 goes into there, 8 goes into there, 6 goes into there, and 6 goes into there. 2 minus 1 is obviously 1, 7, 5, 5, and this works, right? So this works. So this one works for both the red and the green. What about this one? Again, we'll put K1, K2, K3, and K4. Now, does this work in the green? Put them in, minus 4, minus 1, minus 4, minus 1, 6 minus 1, 6 minus 1, minus 5 times minus 5 times 5 times 5. This doesn't work. That's not correct. So we've eliminated this one from contention. And because this one is the only other one we have left, and you can test it if you want, pause the video, put it into the blue one now, but these are the only 4 things that work for all of them. So this must be the correct answer. These must be my k's. So going back all the way to the start, this is my function. It splits off into factored form with these k's here, but now I know these are my k's. So that's my factorization. Now, you haven't got quite full marks here, just be careful because it says find the roots. And I've talked about it before, k are not the roots, but they do help you find the roots. The roots are minus 2, minus 6 repeated, and minus 8. And we're finally done with the question. Really, really amazing job if you stuck through all that. It's a fantastic question using so much good maths. Yeah, very university like that question there.